we have finished yesterday. We have finished discussing sections 17.1 and 17.2. Or today, we shall discuss the continuation of chapter 17, which is section 17.3. Now, 17.3 talks about the Wishart distribution. We have discussed this in the univariate case. So now we will look at on the multivariate case perspective. So we can think of the Wishart distribution as the generalized chi-square distribution. So how did we obtain the generalized the chi-square distribution? So we shall recall in the univariate case. So you start with a random vector which is normally distributed, standard normal with mean vector 0 and variance 1. And if we we try to transform this x into a quadratic form, that is x squared. We call that a new random variable y. Then the y there is no longer normally distributed, but it will become a chi-square distributed random variable. Now, for this particular case, since this is in the univariate case, so the chi-square test is associated with degrees of freedom, and with this case, it is just 1 degrees of freedom. So, in short, we can write y to be chi-square distributed with 1 degrees of freedom. Now, later, we shall introduce, this is assumed when you put your degrees of freedom there, that is assumed that it is central chi-square. But later, we shall introduce a non-central chi-square. So generally, we usually write it in this manner. And here will be the centrality parameter. Okay, if the centrality parameter is 0, so we just delete this part and we write it in this manner. The centrality parameter is usually denoted by delta. So if the random variable is not central, so it will have a non-centrality parameter denoted by delta. So we write it in this manner. So in general, so if we have x of I to be standard normal distributed, and we define x squared as the sum of the squares of each of these random vectors here, then this will become chi-square distributed with n degrees of freedom. Again, this is not the centrality parameter, so this is in the univariate case, basta sa univariate case magod center na tanan. So in general, we write it in this manner, and this is the non-centrality parameter. And if the x's now will have, so it's no longer standard normal, but it has a mean mu I and variance sigma squared I, then this transformation here for your x, so this is square deviations from the mean divided, standardized by dividing it by its variance, or this type of transformation of your x. So take note that your x's here should be normally distributed minus the mean. So this is central. This is what it makes it central. Kaya subtract man nimo from the mean. So it is chi-square distributed with n degrees of freedom. So let's now have the multivariate case for the chi-square distribution, and it will become now what we call the Wishart, no? Wishart distribution. So we have a random matrix X. So take note that this is a vector, no, not an individual X sub 1. So it's a vector. This because n by p, X is n by p. So you will have p elements or p columns, no, because this is n by p, and which is normally distributed with a mean vector mu. The psi or the covariances among the rows will just be the identity matrix, and sigma will be the covariances in the columns. Among the columns, the column variables will be sigma. And x sub i's, each of these are independent. That's why we can assume psi here to be just I because of this assumption. And each component there is still normally distributed. So we have a result yesterday that if the whole matrix there is normally distributed, then it follows that each component is also normally distributed. But the other way around is not necessarily true, except for some conditions. Now we define a new random variable W, which is x prime x. So x prime x will be something like this. X prime will be x1, x2. Now take note that these are vectors, no? So when we multiply this is just the summation of x. So this is primes. So x prime x1 plus x prime x2 and so on and so forth. So that is the summation of x prime I, xi, I from 1 to n. Take note that each of these is a vector of 1 by p, no? So p by 1, this is p by 1 and this is 1 by p. So this is a p by p summations. Summations of a p by p matrix. So then W is said to be Wishart distribution. So W is a P by P random matrix. So from X, which is N by P, W will be P by P, and it is not a non-negative definite matrix. Now, one result, lemma 17.5, tells you that your W here depends only on mu. So take note from X, which is normally distributed with a mean mu, I, and sigma, X prime X, which is W, will be dependent on a parameter mu prime mu. Later on, this mu prime mu will be actually your delta, which is the non-centrality parameter. So remark, with this lemma in mind, we say that the distribution of W is a p-dimensional Wishart distribution with n degrees of freedom. on the covariance matrix sigma, and with a non-centrality parameter mu prime mu. So that we write uh, the general case of your chi-square distribution, W here will be Wishart P by P, and then there will be n degrees of freedom. So the first component is a degrees of freedom. The second component is your variance for the columns, or the covariances for the columns that explains the columns, and the non-centrality parameter delta. Note that both your sigma and delta are non-negative matrix, non-negative matrix, non-negative definite matrix. Okay. So if your delta is there is zero, or the non-centrality parameter is zero, then we say that W is central Wishart distribution, and we only write this in this manner. So if it is not equal to zero, then we say that W has a non-central Wishart distribution. So in general, you write it in this form. This one. Okay. So let's have the first theorem. This should be familiar to you. Because we've discussed Wishart distribution in chapter 3. So let me scan first an equivalent form of that. What chapter did we study about Wishart? Did we study about Wishart in the univariate case?
Parang wala po.
Murag wala, ma'am.
Chi-square lang, ma'am, ug spherical normal.
Okay, chi-square. Where is chi-square? Okay, here. Because this has a similar form. Let's delta and sigma plus delta. Asa na ako nakita? Anyway. So let me do this. Kay square siya taman, kay univariate man to. So ang generalized type niya is the Wishart. Okay. So what is this theorem telling us? That if we have a random matrix which is transformed as x prime x, say assumption sa x is normal with mean mu and I and sigma, no? Muna ang assumption nato. Human atong gi-transform na. Okay, of course, the xi's should be independent and each of the xi's are also normally distributed. So if we have a transformation from a normal to x prime x, it becomes Wishart. So suppose that it is already Wishart with this parameter n, sigma, and delta. Okay, so delta here is mu prime mu. Then it tells you that the expected value of W is equal to n times sigma plus delta or plus mu prime mu. Okay, so let's look at the proof. So we know that your W is x prime x. You get the expectation of that. And you know that x prime x can be written as the sum of xi prime xi, where each of the xi's here are independents and they are normally distributed with mean mu I prime because this is x prime and variance sigma. So, wala si I din or wala si psi, no? Wala si psi kay kada xi man no? Because when we are talking about I or the psi, it is talking about covariances for the different rows man. Isa ra man kada isa man sa ilaha. So it's just a component of the mean mu I plus and the sigma and the columns, no? Kay naaman ni kay columns. Si x1 manggod is x11, x12 until x1p. Do you follow? So ang variability will be concerned between the columns but no longer among the rows kay siya raman isa. But if we are talking about the whole x there, so it should be normal, naa si mu, naa si I, ug naa si sigma. Okay, so we have this. So from here, so you have here expectation of the summation of xi prime xi, but expectations and summations can be interchanged. And then you have a result in chapter 3 that tells you lemma 3.1. It tells you that the expectation of the square norm of x is equal to the square norm of the mu plus the trace of sigma, where sigma there is your covariance matrix. So note that the square norm is actually x prime x. No? That is how we define the inner product, di ba? The inner product. So you have the square norm of u is actually the inner product of u raised to the 1/2. So if you square that, so that is the inner product of u, but the inner product is defined as u prime u. Okay, so this can be the expected value of the square norm of mu, which is equal to the covariance. We cannot automatically put trace there because these are vectors. So you will have the covariance as is plus this is the square norm of mu, or that is the expected value of x prime I and expected value of x prime. That is your mu prime mu. And then but the covariance of this is actually among the x sub i's is sigma. Then you have mu prime I, mu prime. And then you take the summation of this, each of them. But the summation of the variance there, this is just a constant with respect to the summation sign. So you will have n times sigma. And then by definition, this summation of mu I prime, mu I is just your mu prime mu. But your mu prime mu is your delta. So the expected value of your W, which is a Wishart distribution, is equal to n sigma plus delta. So if you recall, if x is just chi-square distributed, what will be the expected value of x?
N po.
What is n? What is n? What is n?
Degrees of freedom, ma'am.
Okay, it's equal to the degrees of freedom. Okay, because I can always have x is chi-square, say f. So it's no longer n, it's f, no? So you have to specify what is your n. It can be the number of observations, but it should be the degrees of freedom, because the degrees of freedom changes. Sa high n-1 na, depende on how you obtain your parameter, no? Anyway, so that is equal to the degrees of freedom. But when it is Wishart distributed in the generalized form, the generalized form of the expected value of a Wishart distribution is n times sigma plus delta. So you are expecting, when it is just a central chi-square, this becomes 0 and your sigma there is 1. That's why in the univariate case, nag-start yun na siya normal na 0, 1. That's why the x square there, when it is chi-square with n degrees of freedom, the expectation of your x, is n, because this becomes 1 and this becomes 0, no? But in general, n na lang siya. But in general, for a generalized chi-square, or we call it the Wishart distribution, the expected value of that random variable is n times sigma plus delta. Do you understand?
Okay.
So mao ni ang general gyud na formula, no? Kana inyong nabalaan na chi-square na equal lang sa n, actually that is only good if you have a univariate case, no? Or a univariate case plus central siya. Pero kung in general, nice non-centrality parameters, so this is the general formula of generalized chi-square. Okay? So I hope you learned something new. Next, if we have a W or a random matrix which is distributed Wishart, and this time we have a P equal to 1 and sigma is just equal to sigma squared. then the W there will simplify to a chi-square distribution. But you have a non-centrality parameter which is equal to, so actually this is W over sigma squared, W over sigma squared. This is W over sigma squared, and that is chi-square distributed with non-centrality parameter delta over sigma squared. So naan siya. That's why naapon ni siya. Okay. So sometimes the book writes it in this manner. So when P is 1, Wishart becomes chi-square distributed, but this is a non-central chi-square. Okay. So when P is 1, in the individual xi, mabilin siya x1 na lang, no? So, ang katong x nimo, mahimo na lang siyang vector. So, x1, x2, to xn. So, this is still normally distributed with individual mu I. So, kini siya na ay mu1, kini siya na ay mu2, kini siya na ay mun. Sa iyahang mean vector. And you have sigma squared as your constant lang siya. Kaya wala naman siya among the columns, no? So constant lang siya ang iyahang variability with itself. So sigma squared I from 1 to n. So what will happen to your x prime x? So your W, which is x prime x, which is by definition is the summation of xi prime xi, will just be simply the square. So anak man na siya x1, x2 to xn. This is your x prime, then x1, x2 to xn, which is no longer a vector. So it's just the summation of xi squared, I from 1 to n. No? So do you follow? So you have that. And then you use the result of lemma 3.8. So if you look at the result of lemma 3.8, so the assumptions, you always look at the assumption, no? So sa lemma 3.8, and make sure that the assumptions are satisfied. Lemma 3.8 tells you that the excess should be normal with mean sigma squared I. And then sigma squared is scalar. And it tells you that the yi's there are independent and they are normally distributed mu sigma squared. And if you look at the square norm of y, square norm of y over sigma squared, and that is equal to, okay, the square norm is actually y prime y, no? Chi squared and degrees of freedom, and the non-centrality parameter is mu prime u over sigma squared. Now, observe that we can use this lemma since the assumptions here are satisfied for this given scenario, no? So you have these assumptions here. You have this assumption, and then we know how we convert W is from X, which are normally distributed also. So the conversion now satisfies this one, and this one. So we say that W, which is x prime x, similarly, that is your square norm of y. In our case, that is x, and then divide it by sigma square is chi-square distributed, which is here, then mu prime mu over sigma square. So if we let delta to be mu prime mu, then we arrive at what we want to show. Questions?
Wala ram.
Yeah, ma'am.
Okay, so let's proceed. Next result, we do some transformation on RW by pre-multiplying it by a scalar. Let me check if this is, if A equal to 0 is really included. Chapter 17. Okay, the book is quality, so pwede 0. But if you pre-multiply it by 0, everything here will become 0. So it 0 times W. So nonsense man mag-talk about na ay equality, no? Anyway. Maybe it satisfies, but we don't consider an A which is 0 because it will make everything 0. Okay, so we still have this assumption that it is Wishart distributed, and then we do a transformation on a Wishart distribution and look what happens to the parameters after pre-multiplying it by a scalar A. The degrees of freedom is retained. Sigma will be pre-multiplied by A as well as mu prime mu, or delta will be pre-multiplied by A. So that is what is happening when you pre-multiply it by a scalar. So take note that our concerned random variable is AW. Take note that we obtain W as x prime x. So we have to think of a function of x such that the result is AW. So that function now will be something like this. So it will be A raised to the 1/2 x prime. Since A is a scalar, so A to the 1/2 prime is still A to the 1/2. No? So actually, ang imuhang kanang x dinhin na gusto is A to the 1/2 x prime man A to the 1/2 x. Are you following?
Yes, ma'am.
Oh, para mahimo na siyang A to the 1/2 prime A to the 1/2 man x prime x. But A to the 1/2 prime is just A to the 1/2. And then mahimo siyang A x prime x, no? Mao na atong gusto. Gawas kay si W manggod kay x prime x. Okay, do you get the point? Because that will be the usually the technique here, no? To have your transformation. And then your x here is normally distributed. That is how we defined for a Wishart distribution. And then by applying 17.2b, so the one that we use from a normal and then we pre-multiply by a scalar. Do you recall? 17.2. That was only yesterday, no? 17.2b, if we pre-multiply a normal, an x, if we have an x, which is normal, mu psi sigma, and we pre-multiply it by an a, it becomes normal with a mu, a squared psi, and sigma. Okay, so you have an x which is normal. If we pre-multiply it by a raised to the 1/2 x, so it will be, so the a here will be a to the 1/2, so it's a to the 1/2 mu, and then a to the 1/2 square will just be equal to a, but your psi here is just 1, and then sigma. Okay, is this okay?
Yes, ma'am.
Okay. So I told you yesterday na pwede po na siya, it can be shown na instead na dinhi ang, okay, instead na naa dinhi ang a square, pwede po na siya na naa sa psi. So you will have ax to be normally distributed a mu man kini si psi man si a square sigma, no? Because that is just a scalar, so pwede ninyo i-tweak ang moment generating function. So how did we obtain this distribution yesterday? By using the moment generating function, and since it is in terms of a trace, pwede rin ninyo ibutang ang scalar sa pikas na side. So it can also be shown that you can write it in this manner. Now the purpose here is to retain I there and write it in the A in the sigma side. Okay. So if we have this, so our new mu with respect to, if we call this the new W there, so you will have a new mu, we call it mu star. So mu star will be a raised to the 1/2 mu. Sigma star for a Wishart, we call sa Wishart, ang iyang component is n, sigma, and delta, di ba? Okay, so the sigma here, or the sigma star with respect to the new W there is a sigma, and your x, generic man gutaga x prime x, pero AW man ta, so murag tag nangita og x star prime x star. So ang W nato generic is x prime x, pero AW man ta, so dapat nangita tag x star prime x star, no? But ang atong x star now will be a to the 1/2 x. So this will become a W star, which is x star prime x star. And x star is normally distributed with mean, mu star, I, and sigma star. So nag-satisfy ni sa tanan requirements for a Wishart distribution, so that it follows that our W star which is actually our AW, will be Wishart with parameters n, sigma star, but recall the sigma star there was A sigma, and delta star will be mu star prime mu star. Now, our mu star is a raised to the 1/2 mu. So if we try to compute this one, so mu star prime mu star is actually a to the 1/2 mu prime a to the 1/2 mu, but this is equal to mu prime a to the 1/2 prime a to the 1/2 mu, but this is just scalar, so a to the 1/2 prime is just a to the 1/2 times a to the 1/2, that is a, and then you have mu prime mu, no? So and that is equal to a delta, which is this one. So your W star, which is actually a W, is Wishart with these parameters. So always remember that W is x prime x. So if you do some transformation on W, make sure na mangita mo o component na i-prime ninyo times that with respect to x, which is a function of x, no? A function of x. Para mahimo siyang Wishart. Okay? So this is your new W star, whatever is the form that you want to show that it is Wishart. Okay, so this is another transformation, AWA prime. So it starts with a Wishart, and then you have a matrix here. So this is K by P, and then your prime will be P by K, and your W is P by P. No? So this is conformable. So again, ang among W is x prime x. So ang imong gusto is AWA prime. So unsa kay times ana as a function of x na mugawas AWA prime. So kumusuhay ka og AX, sa may mugawas ani x prime x prime A prime AX. So dili. Ini man imong gusto. Kung balihon nimo XA prime XA, naman kang A prime X prime X A. Gyapon. So unsa man ato ang himuon ani. So kay di man gyapon mo gawas. So unsa man gyud ang component de ani. Okay? So mao na ang pangitaon. So in this case, it should be AX A prime. XA prime. So kung XA prime, i-prime name mo. So, and then multiply it by XA prime. So, unsa may magawas? A, X prime, X, A prime. So, kini na component di ay XA prime. Gets ninyo?
Yes, ma'am.
Di ba ganina kay gadula-dula ko sa unsa ano na ax prime man ax, di ba? Wala man to ga work. Or nagdula po ko sa xa prime, xa man dili man siya equal sa awa prime. So the correct term is xa prime para mo gawas ning a x prime x a prime, which is awa prime. Correct? So this is what I'm pointing out. Okay, I hope you understand. You got my point. Question so far? Wala. Okay. Do you still understand?
Yes, ma'am.
Yes, ma'am.
Okay. So these are the given. You have a matrix K by P. A conversion for it to be short is x prime x. Sa gani ang x, normal. No? Nagini na assumption ha. Normally distributed. And then a linear function of x will be x a prime. We chose this because our aim is to have aw a prime or a x prime x a prime. Okay, so let's look at the mao man ang ato ang x star, no? Ang atong x star is a x a prime. So ang atong w star na gusto buhaton is x star prime x star, which is your ito a prime w a prime ano bali a x star aw a prime. Atong w is x prime x. So awa prime is our w star. So let's look at the distribution of xa prime. So we use 17 point D. 17 point D is transforming x, which is normal, and we pre-multiply it by matrices C and D. So if we recall, 17.2D tells you that if we try to transform an x, which is normal, mu, psi, sigma, cxd plus e is still normal. The parameters will be c mu d plus e, c psi, c prime, and d sigma d. Okay, so in this case, our c is just the identity. Our d is a prime, our e is 0. So this will become 0. This becomes the identity. So what will happen is mu a prime, because this is a prime. Let me change. So this is a prime. So this will become a mu a prime. C is identity. This is identity. So what will retain is psi, which is just I, which is this. And D is A prime, sigma, then A prime. So A prime prime, which is this, sigma A. So XA prime will be normally distributed with parameters mu A prime, I, and A sigma A prime. So that is using the result 17.2. So this is okay. And then this will become your mu star. This will become your sigma star. And your X star will be XA prime. So since everything on the assumptions of a Wishart distribution will be satisfied, one is X star is normally distributed. So with a mean mu star I and sigma star. So take note the form of your mu star and sigma star. So this implies that if we get X prime X or X stars prime X star, it becomes Wishart. Take note, you have to check the dimensions of your X now. So this time X star will be, because it will be dependent on your A. Your A here is K by P. So if A is K by P, so that is K by P, Wishart is P by P, and A prime is P by K. So the dimension now will be a K by K. So that's why your term here in the denominator, in the subscript of Wishart, which talks about the dimension of your W star will be K, because that is a K by K now. And then N, sigma star, and delta star. So W star will be AW A prime. Your sigma star will be A sigma A prime. And checking on the delta star, wherein your mu star will be mu A prime. No, that is your mu A star here. So you get mu star prime, mu star. So this is mu star prime, mu star. And then you will have A delta A prime. So delta star will be A delta A prime. So in conclusion, you have a transformation AW A prime is Wishart and A sigma A prime and A delta A prime. So in summary, I want to emphasize W X prime X, that all assumptions should be satisfied. That is, X should be normally distributed. No, you have to look at what will be the parameters of your X. So mu, psi, and sigma. So if you transform now into a new W star, which is X star prime X star, you have to check X star should be normally distributed and what will be the parameter. So if you satisfy that, you X star prime X star will be Wishart, and check what will be N, sigma, and delta. sigma star and delta star, no? So that's the flow when we try to find out what is the distribution of the quadratic form of a random variable. And be careful on its dimension, because it's not always n, it's not always p. It will depend on the dimension of your transform variable. Question? So for the two proofs, you have seen the flow, no? The flow of the proof. That is how you do it. Next result will be partitioning of your W, but we will have a 10-minute break first. Do you have question? Stop recording. Okay, so let's continue. The next result deals with partitioning our random matrix, which is Wishart distributed with these parameters. So suppose we have this partition here. It follows that you have to partition also your sigma and your delta. So if this is P, so your W is P by P. So partitioning will be with respect to a K by K. So the rest of the partitioning, if this is P by P, so and this is K by K, so this one will be K minus P by K. This one will be K by K minus P by K minus P. Tama ba? And this one will be number of rows. This is K by minus P. Oh, anyway. Like determine ana. Basta kini is K by P. This is P by P by P. So kini din will be, ang nabilin is K minus P. P minus K, sorry. It should be P minus K. So it's P minus K. Mandinhi pod. This is by K. Kay K ram ni ka columns. Bini. There will be P minus K columns. Pila ka rows? K, no? K by P minus K. Are you following? Kini siya will be P minus K by P minus K. Correct na?
Yes, ma'am.
Just follow through it. If that is how it is partitioned. Okay. You have here a marginal. So here P minus K. The marginal distribution is still Wishart. No? So if we have a whole matrix which is Wishart and we try to partition it, it's still Wishart. No? So W11 is still Wishart with these parameters and sigma 11 and delta 11, and W22 is still Wishart with these parameters. Okay, so I will leave to you the proof of this distribution. I do not know if the notes have a detailed proof of this. Anyway, this is just similar to what we have done in the univariate case. So you just look into it for the chi-square. Now, let's go to another result, but this time it is but this time it is with respect to projections on V. So we start with the assumption that the x's here are normally distributed. Your x is n by p with a mean mu I sigma. You have a subspace V, which is k dimensional. So k is less than n because it is a subset of R to the n. Then x prime PB x will be Wishart with degrees of freedom k. So it will follow with the dimension of your subspace, ang degrees of freedom, but the dimension of your x prime PBX, x prime is P by N. So again, PB can be related to a matrix. So this is N by P. So your expectation of your PB should be N by N. We have a comment there in chapter 2, I think, that PB here. We also use PB. There is in page 35 of Arnold. We also use PB for the matrix of the function PB. No? So we can relate PB as a matrix. So we are assuming that PB here should be N by N for this term here to be conformable. Here, for it to be conformable. So the degrees of freedom follows the dimension of your subspace. You have sigma here, and delta will be mu prime PB mu. So we think of x star such that mugawas ni, no? Ang ganina sa atong matrix AWA prime, but this time it's x prime PBX. So what will be our x star? No? X star prime x star. Nana ang prime sa ibabaw. So ganina kay sa to atong gigamit AX prime, no? So kung naa diha, can it be PBX or PBX prime? Yun sa atong x star. PBX prime PBX. So magawas ka na. That will be x prime PB prime PBX. And can we write PB as PB? Yes, if we assume and if we know that PB prime is just PB and PB squared is just PB, which is, we know that this is true. Correct?
Yes, ma'am.
Property. So ang atong kandidato day ani is PBX. So we will see later in the proof kung PBX ba gyud ang gamiton ani. Alternatively, if A is an n by n idempotent, so idempotent, sa ganitong idempotent, it is idempotent if A prime is A and A squared is A, no? That is the definition of an idempotent matrix. And the rank of A is K. It means it carries the dimension of your V. then PB here will become your A, and it is Wishart K. Pareha sila. So, ibig sabihin, once ma-prove na to, kinina case, it follows that if we will let A have these following properties, that is, A is idempotent, so it satisfies these conditions, and then it has a rank K, so that it will follow the dimension of your V. It will also be Wishart. So X prime AX will be Wishart. So let's try to look at the proof. So to prove this, we have to assume an orthonormal basis because recall, kinibitaw na condition sa una na atong ginagamit. This has a condition na kung ang atong X is orthonormal na. Correct? Do you remember that? Kinina condition, tinuod lang ni siya kung atong basis matrix is orthonormal. So to prove this, we have to assume that we have a matrix which is an orthonormal basis for V, so that we can use we now use a transformation U prime X. So to ato ang itsura ganina sa atong kandidato PBX. So U prime X. Okay, tanaw na to ang distribution sa U prime X kung orthonormal basis siya. So katong transformation ni siya na CXD plus E, no? But this time, zero lang ni man kini identity. So nalang ka sa CX. Normal siya. C prime mu D man to, no? Plus E. Normal. C, una ang prime. C prime C. D sigma D prime. Let me check.
Bali ang koan na. Si psi C prime.
Ulahi ang ano. Okay.
Yes, ma'am. Then sa D, ma'am, kay una ang D prime.
Okay. So you have C psi C prime. And then D prime sigma D. Is this correct?
Yes, ma'am.
Okay, so in here, C will be U prime. So what will happen here? This is just identity. So correct na ni siya. This is U prime mu. And then psi is identity. So C is U prime. So this becomes CC prime, but our C is U prime. So U prime prime, which is U prime U. Okay, so this is correct. And then D is identity. So this is just identity and identity. So what remains is sigma. So this is correct, no? Using your 7.2D. So this is the distribution of your U prime X. But since U is an orthonormal basis, then U prime U is just the identity because it is orthonormal. Ortho means terms of dissimilar is 0. Normal means when you go get the inner product of two similar, it is equal to 1. So what will happen to this? All the entries in the diagonal matrix will be 1 and the off diagonal will be 0. Okay, so that will be identity and then sigma. Do you follow? Is this okay?
Yes, ma'am.
Okay. So ang iyang gilet na x star is u prime x. So it follows that mu star is u prime mu. Okay, so by definition of V short, we have to satisfy, so ganito kinahanglan i-satisfy ang atong mga x star normally distributed. Mao ni atong x star, no? Si mu prime x. So para mukuha ta og w na x prime x, pero ang ato ang ano din is w star, which is x star prime x star. So ang atong x star is mu prime x. So that when we do x star prime x star, mu prime x, and u prime will be our PB. So that is the definition of PB. Let's have theorem 2.6b. Okay, so if you recall, pag naana kay x na orthonormal basis, pinumdum mo ani, theorem 2.6. Ang assumption ani, take note, you always look at your assumptions kung na-satisfy before you use any theorem, ha. Ang assumption ani, ang x daw orthonormal. No? And then pag orthonormal na, si x prime x is I. So mao to nahitabo ganina. Sa ato ang u prime u is I. Okay? And then ang letter B, this is letter A. Ang letter B, siya, ang PBY is x prime y. So ibig sabihin, u prime is your PB. Are you following? And then C is the square norm of projection of y onto V is just equal to x prime y square norm. Okay. So that is why we chose this u prime x, no? Because we want to use this theorem 2.6 na PB. So x prime ang PB. Okay? So we see that the x star is normally distributed and x prime x is actually x prime PBX. So what we have shown here is that x prime PBX is Wishart, K, sigma, and delta star. Now let's look at delta star. That will be mu star prime mu star. So this is delta star, mu star prime mu prime, which is equal to this, but this is your PB. So the final answer for your W star, which is x star prime x star, which is x prime PB, x is Wishart, degrees of freedom K, sigma, and this is your delta. So your x star was u prime x. Okay, this is your x star mu prime x. Questions? So we are done. So the trick here is to know that u prime is your PB, where u is orthonormal. Do you have questions? Can you still hear me?
Yes, ma'am. Amen.
Okay. Now, what happens when we have an idempotent matrix here A of rank K? So, since idempotent satisfies the conditions that PB prime is PB and PB squared is just PB, it follows that changing PB by A, you will still get this distribution. So on the condition that A should be an idempotent matrix and it has a rank K. So it follows the dimension of our subspace. Okay, so next. This is familiar to you because this has an equivalent result in the univariate case. That will be theorem 3.13. So 3.13 tells you that AY, so the condition here is Y normal mu sigma squared I. Sigma squared is positive. And then you have two matrices, AB and CD, which should be conformable when we multiply it by Y. So these are independent if and only if AB is 0. And then, so actually this is similar to this, no? AB prime is 0. So actually pareha ra gid sila, but this time you have an X which is multivariate in nature. Here, you have a Y which is univariate in nature. Then if AC is 0, then AY and Y prime CY are independent. So this second result in theorem 3.13 is very useful in showing the mean and the standard deviation are independent. So if you want to show that the mean and the standard deviation S are independent, all you have to do is to rewrite X bar as AX and rewrite S square as Y prime CYY, no? Because if you recall, S square is a function of the summation of yi squared, no? So, mo ni ang component of Y prime Y. So if you can rewrite this X bar as a component as AX, so you have a matrix A or a vector A multiplied to X, and you can rewrite X ni, and you can rewrite the variance as X prime times some matrix here times X, and if you try to multiply A and X here to be 0, if that is 0, then we say that X bar and S squared are independent. This is usually the purpose of this theorem there, or that result. So this time, in the multivariate case, it has an additional assumption. The additional assumption is that B should be positive, non-negative definite matrix, and then AB is 0. Then it will imply that AX and X prime B are independent. So this is the added conditions. And then theorem 3.13c tells you that if CD is 0, then Y prime CY and Y prime DY are independent. So in here, added conditions is that A should be non-negative positive definite matrix, non-negative definite matrix, and B is also a non-negative definite matrix. And then AB is 0. Then this form here. So if you can rewrite two. So univariately makita ninyo na kini a function of xi square ni siya. Kini pud a function of the summation of xi square. And then naa kay matrix component in between. So that if you can show that the product of A and B is 0, then we say that the whole thing here are independent. So multivariately, this second result here, B2, is used when you want to check whether the mean and the variance here are independent. So all you have to do is to transform the mean as AX na itsura. You have some matrix there. And then you transform S as X prime X. So if you recall in your linear models, we have shown that in the coordinatized version of the linear model, we have shown that your mu can be written as AY, and then your n minus p sigma squared, your variance can be, the estimator can be written as y prime I minus x prime x inverse x prime and then y. Mo ni akong ginapasabot kana siya mo na ay moang b, no? And then unsa man ang itsura sa mu kung ay, unsa imong a? Unsa imong a?
EV,
Anybody?
ma'am.
Ha?
EV po.
Unsa to? Unsa imong ibutang sa A para may mo siyang ang mu nimo may mong AY. Unsa may usual na X bar na lang. 'Di ba ang formula sa X bar kay 1/n summation of X sub I. So unsa man ang imuhang or di na lang Y bar akong gamiton para delete sa Y. 1/n summation of Y I. So unsa man ako ang X bar, unsa man akong or mu hat. Hat man gud akong gigamit ini. Unsa man akong mu hat na AY ang itsura, unsa akong A?
EV, ma'am.
Ha?
Over N, ma'am.
Sa to? Ay, gasulti 1 over n. Pero unsay
1
itsura
over
sa
N.
1 over n? Dili man ka pwede kay kini siya kay vector man eh. Vector man imong y. So, ana man na itsura y1, y2, to yn. So, unsa imong a?
1 over N times identity, ma'am.
1 over n identity. Is that correct? So, unsa man ang 1 over n times identity? So, kung 1 over n times 1, 1, 0 diha. This is a constant. So, ang mugawas ani, kung identity, unsa man ni, n by 1. Pag mag-identity ka, square matrix man na. So, n by n. So, ang mugawas, n by 1. N by 1. So, unsa man mugawas ani? Sakto ba inyong 1 over n times identity. So, mugawas ana kay ang entry din ni 1 over n, 1 over n, 1 over n, 0 diha, man i-times nimo sa y1, y2 to yn. So, this is n by n, this is n by 1. Mugawas ani is n by 1. N by 1 na x bar. So, kini siya times diha, mugawas ana is y1 over n plus y1 over n. Okay. Or pwede po na 1 over n, 1 over n, 1 over n, di ba? Times y1, y2 to yn. You multiply that. But it becomes a scalar lang, dili matrix. So it should be multivariate case man eh. So it should be 1 over n times I. So if this is your 1 over n times I and you try to multiply it, if that is your A, and you try to multiply it by B, and what you will get is 0, then we say that mu hat and sigma hat are independent. Do you follow? That is how you prove it. No? Anyway, so multivariate case. So it should be 1 over n times I. Kung univariate lang, it's just the vector of 1 over n. N by 1 na 1 over n. Okay? So, the proof are similar to what we have done in the univariate case. So, I will leave it as your exercise. I do not know if the notes have proofs. Just check. Okay. Next, theorem 17.8. So we have this assumption that X is normally distributed. But this time we are strict on the assumptions on your psi and sigma. It should be positive definite. The reason for that is, can you tell me? What is the possible reason for this? Why are we strict in this assumption? But why do you think we will be strict on this assumption? Anybody? Okay, Sorongon tells me that to be invertible, ma'am. Okay, so because later in the proof, it will use the concept of the inverse should exist, no? So correct si Sorongon for it to be invertible, or the an inverse of it should exist. So it will be used later in the proof, no? Existence of the inverse. Okay, so how do we interpret A? So if n is greater than or equal to P, or P is less than n, so ibig sabihin we are looking at the rank, no? The rank, the minimum between n and P. So if n is greater than or equal to P, then the probability that X has a rank P, as long as this is satisfied, is 1. So we are almost surely, almost sure, no? Almost sure ni siya, because the probability is 1 na ang rank ani na X is equal to P. And next, if A is a vector n by 1, not necessarily 0, the 0 vector, and if n is strictly greater than P, or P is less than n, and we are considering the rank of X is P, then the probability that this is true is 1. No? So ibig sabihin, sure you ka, no? Na ang joint matrix with X and A, so partition na siya na kay A na n by P man imong i-join sa X, that is your matrix. You have an A and X, no? And you know that the rank of X is P, so you just add one more plus 1 for the rank to cater for your A. So the rank of a matrix wherein you adjoin A to X is P plus 1, and you are almost sure with that. The rank of A X, or X adjoint with A, will be P plus 1. The probability of that is 1. So ibig sabihin, that is almost sure. Sure ka. Na basta mo satisfy lang ni ng mga conditions. This one, and this one, no? So as a corollary to that, if we have a Wishart, which is a random matrix which is Wishart distributed with this parameter n, sigma, and delta, and if this assumption is satisfied with this assumption, then the probability that this matrix here is positive definite is 1. The probability that this random matrix is positive definite is 1. So what's the importance of this? So when W is positive definite, and you are almost sure of that, it means that the inverse of W exists. No? Okay, positive definite man siya. Ibig sabihin, it is invertible. We want this result. So this is the assumption for this result, that the inverse exists when these two here are satisfied, because we are going to use W inverse later in this important lemma. Okay? So if these two conditions are satisfied, then we are assured of an inverse of W. Okay, so if sigma is positive definite and n is greater than or equal to p, then W is invertible, meaning W inverse exists with probability 1. And we call W as non-singular Wishart distribution. So we ignore the null set in which W is not invertible, and we assume always that the inverse of W is exists. No? So for that to happen, we always assume these two. Okay, that two conditions. So W is invertible if these two conditions are satisfied. Okay, so the next section will be 17.4. So we will be back. Stop recording.
Yes, ma'am.
Can you see my slide?
Opo.
Yes,
Yes,
ma'am.
ma'am.
So let's continue. So this time we will have section 17.4. So 17.4 talks about some deeper properties of the Wishart distribution, some more property, and Arnold just labeled it as an important lemma. So in this lemma, we assume that you have a random matrix, which is Wishart. Delta is not stated here, so it means that this is a central Wishart distribution. No? So it means that your delta here is equal to 0. So it is just a random matrix dependent on the parameter degrees of freedom and just the covariance between the columns. And we assume here that n is greater than or equal to p. So it means that if you have this assumption that the rank of x, the original x before we have x prime x there in your W is equal to p. And we want sigma to be positive definite. So if this is positive definite, then the inverse of sigma exists. And because of these two assumptions here, we will be sure that the inverse of W also exists. So now we do some partitioning on RW. This time, Arnold uses the dimension as Q by Q, and W is P by P. So you know what will be the corresponding dimensions of these components there, as well as for your sigma. So for simpler notation, what Arnold did is to have T to be W22. So this part here, he just denoted this by T, and U by W22 inverse W21. Now, if you recall, how do you get an inverse of this kind of matrix? So in your appendix, let me scan through first. how do you have a general inverse of a matrix? Okay. So in page 140, oh, 450. You have a lemma there, A.2. That is, if you have a partition on S of the form S11, S21, S12, and S22, you can get the inverse of this matrix, S inverse here, will be equal to V11, V12, V21, V22, where V11 inverse is equal to S11 minus S12, S22 inverse, and S21. No? So the inverse of this is equal to that. So that actually V11 is S11 minus S12, S22 inverse, S21 inverse. No? So you can scroll to that page 450 to review the forms of an inverse of a matrix, because we are going to use this here in the proof or in the discussion of our lemma. So what I want you to know is to be familiar of this form. Mo ni siya. Okay? So by notation, mo na ang sulod sa imuhang W, di ba? Ang sulod sa imong W is W11. Okay, let's just go back here. Ang sulod sa imuhang W is W11, W122, and T, W22. So, looking at this form, kining W11 minus W12, W22 inverse W21, you know that V there will be the component of your W inverse, no? Imong W inverse. O na imong W11 sa inverse V. Are you following? Kini ba? Kini na term. So mo ni kandidato sa W inverse. Ang sulod niya katong dinhi V, no? So V1, V2, V3, V4. Anyway, mo nang sulod, mo na si V. Component na siya sa W inverse. Now, as what I have told you earlier, since these conditions here are satisfied, sa kani assurance ani na conditions, kining duha ka conditions are satisfied, we are assured of an inverse, no? So ibig sabihin, ang sulod sa imuhang W inverse, which is katong mga sulod sa imuhang W, W11, W12, W21, and W22. Na siya corresponding, kung kwaon nimo ang inverse, napod na siya iyang corresponding inverse. And the notation of Arnold will be in terms of U and V. U and V. No? Now, this lemma tells you that okay, let me go back to this. So this is Wishart, no? This is Wishart. This lemma tells you that kinesi W22 is also Wishart, no? But in terms of the inverse, naman ay component din V. So V, o kabaloon sa notation ni Arnold na sa iyahang uban na data din Pero this V here, conditioned on T, U, si U. I think U is here, kini, sa inverse. Let me check, ha. Itsura sa inverse. Inverse of a matrix V22. Yes, is inverted. So kung invertible daw ang example, we know that W is invertible. So W inverse exists. And if W is invertible, it's still page 440. If W is invertible and you know W is W11, W12, W21, W22, then W can be written as, the determinant of W22 times W11 minus W12, W22 inverse W21. So we can express W. So if this is our original W and W is invertible, we can express W as in this manner. So the determinant of W22, finish siya, which is your T by notation, then times the determinant of W11 minus W12, W22 inverse, and W21. So, and it is also with the condition that dili si W ang invertible but si W22. Okay, if W22 A, lemma A.2. If W22 is invertible, then we can write W in this manner. Okay? If W is invertible and the inverse exists, then, okay. Ang next, kato akong gisulat ganina, if W is invertible or the inverse exists, invertible. And then W inverse will have the components V11, V12, V21, and V22. Then VW, kini daw na component, inverse ana, can be written as W11, ito akong gisulat kanina, W12, W22 inverse times W21. No? Pwede nimo isulat ang inverse sa kini-kini na component there. One more result about the inverse. Kana siguro ang gamitin. So let's have that. So let's have this. So again, our W is of the form W11, 12, 21, and 22. Arnold transforms this to W11, W12, W21, and T. This is the notation. And then U is equal to W22 inverse, W21, and V. And V, if we have an inverse here, V is here. No? Ato akong gisulat. Kini V, no, V inverse. V11 inverse. So if this is V, V inverse is W11 minus W12, W22, and W21. Okay. So if we look at the distribution of T, conclusion, no? The distribution of T will be V sharp, P minus Q. Okay, mao man ni ang dimension din sa T, N, sigma 22. Then the conditional distribution of U given T, U is this one, given T will be normal with these parameters. This is your mu, this is your psi, and this is your sigma. And the conditional distribution of V given the joint of U and V, we will go back to Wishart. This is the degrees of freedom. And this is central because what you have is just a component of sigma. So this is central. Delta here is 0. We will see the application of these results. So the proof of this is given in Arnold, but I will emphasize the discussion on its application. Okay, so just take note that T will be Wishart, this one will be normal, and this one will be Wishart. And let's have its application for the coordinatized ordinary linear model. That is when the case Q is equal to 1. So unsa gani ng Q? Asa gani na makita ng Q? Wishart is P by P, so Q will be this one, no? Ang imuhang W11, no, is 1. So what will happen? This will be a 1 by 1 matrix. This becomes a 1 by 1 matrix. So when Q is 1, it becomes the ordinary linear model. So consider the case when Q is 1. That is when W11 and sigma 11 is 1 by 1. Then dili na ni siya bold. Okay, 1 by 1. So equivalent to your linear models, the beta can be expressed as sigma 2 to inverse sigma 2 1. So kanang beta nimo mao na ang imuhang U. Kini siya. No, na component with respect to sigma. Okay? Sa imuhang sigma parameters kini. So that is your sigma 2 to inverse sigma 2 1, and then your sigma is equal to this. This is familiar. This should be familiar to you because that is the result of the conditional distribution here in theorem. Okay. Here in theorem 3.7. You have there some assumptions that sigma 2 is positive definite. Then we were talking about the conditional distribution of y1 given y2, which is normal with parameters. Okay, so your y1 is normal, mu1, sigma 1, 1. And your y2 is normal, mu2, sigma 2, 2. And then the conditional distribution of y1 given y2 will be normal, mu1 plus sigma 1, 2, sigma 2, 2 inverse. And then y2 minus mu2. And then the variance is sigma 1, 1 minus sigma 1, 2, sigma 2, 2 inverse, and sigma 2, 1. So that is your variance. So this is actually your variance. We denote it by sigma squared. Okay. So beta is P minus 1 by 1 and sigma is just 1 by 1 because Q is equal to 1. Okay, so the joint of y and x is still normally distributed with mean 0, psi 1, and sigma. So that applying 17.2G on this conditional distribution, you will have this as your mean. So if you recall, what is 17.2G? 17.2G tells you on the distribution of similar ani sa univariate case. Univariate case, multivariate case ang 17.2G. Assumption is still sigma 2 is greater than 0. Then you have some assumptions on your x, which is normally distributed, mu, psi, sigma. The x1 condition on x2 will be normal, mu1 plus x2 minus mu2, sigma 2 inverse, sigma 2, 1. So this is actually your, this part. And then psi. And then similar to this here, no? Pareha na siya diha. So ibig sabihin, if you look at this becomes mu1 plus mu1 plus this component, and then this is by notation is your beta. So if naitabo din ni. So this component here ni x, kini siya as is naman ni siya kana, no? So this becomes since mu there is just 0, makancel ni siya. So what remains is the x2 or just your x, okay, given x2 man. Are you following? Gubot na kayo ako ang tuyok-tuyok din. Okay. Are you following? Because this is just 0, this will become 0, this will become 0. So kining x2, condition on x2, condition on x, mo ni si x, then times this one. And then I, psi, and sigma will retain this one. So that using the important lemma, you know that the conditional distribution of y given x is normal with these parameters. So x beta, beta man eh. This is beta by notation. By notation. So that is x beta I, and then by notation sigma is katong taas na component, which is this one, no? Sigma 1 1, or this one, sigma 1 1 minus sigma 1 2, sigma 2 to inverse sigma 2 1. That is simplifying the terms in terms of beta and sigma. Therefore, the conditional distribution of y given x is just that of the coordinatized, this is coordinatized, not coordinated, coordinatized linear model, which is given in page 65 of our node. And take note, your x will be n by p minus 1 with rank equal to p minus 1. The minus 1 here is a corrected number of dependents, no? Kay beta man ang atong estimator. So now we look at mao naman ni atong x. Kining joint. Okay, this will be our x. So we try to do an x prime x to check for a Wishart distribution. So this is our component yx, no? Get the x prime x. You have this component as your w, and you have this W2 to inverse W21. So ibig sabihin kung kinina ato ang W, x prime x, or really x prime x ni siya din hi. Kini siya mao ni atong component sa W11, W12. This is our W21 and this is our W22. So if we try to look at this, substitute W2 to inverse, so that will be x prime x inverse here. And 21 is x prime y. That is actually your beta hat, no? In the coordinatized version of the linear model. Do you remember this? That beta hat is x prime x inverse x prime y. And then our v, by definition, which is this, substitution on our w here, you get the w there. So regression man is, so ang atong gihimo, gi-append na to ang atong y o ang atong x, ang atong response variable with our explanatory variable. But ordinary raman, so ibig sabihin simple lang, isa ka y, isa ka x. And then if you try to substitute it here and then do some manipulations on the matrices to isolate y prime and y, and this is your component there. This is by definition is your n minus p rato sa ato sa una, n minus p sigma squared. But then we have to do some corrections on our rank. Subtract it by 1. And this is now your AY. Are you still with me? And this is the form of ABY. So your A here in terms of x's will be x prime x inverse x prime. And your b here is I minus x, x prime x. Kaya katong ganina na atong gisgutan na 1 over ni is just for the univariate case, no? So this is ay, this is y prime by, and they are independent if we can show that if we multiply ab to be equal to 0, they are independent, no? So this is your u and v. U as a function of beta hat and V as a function of sigma hat square. So to prove that beta hat and n minus p minus 1 sigma hat square are independent, all you have to do is to multiply this with this and see if it is equal to 0. If that is equal to 0, then we can say that beta hat and sigma hat are independent. So U and V are independent conditionally on X since beta hat and sigma hat square are independent. But you have to verify that by multiplying x prime x inverse x prime with, you try to do this, I minus x, x prime x inverse x prime. So kung multiply ka ana, mas 0 ba na? Check. Also, since the conditional distribution of u given x, what is u? U is beta, no? U is beta. The conditional distribution of beta given the x's by using the previous result general that is normally distributed, then by substitution now in terms of the components of our, this is your sigma squared, and then this is your beta. So by substitution now of how you denote it, so you have the u given x is equal to this one, but u given x, our u is our beta hat. So beta hat given your explanatory variable is still normal with these parameters. So this is your ordinary regression model. No? This is your regression model. This is beta hat conditioned on X. That is the usual way you interpret your regression model. It is conditioned on the explanatory variables, which are fixed. And in expectation, beta hat goes to beta. And with this variance. So in general, sigma squared ra ato actually makita ana if it is an unbiased estimator. But if it's not unbiased, then the variance is a factor A inverse sigma squared, no? So, or sigma squared inverse. Naa siya a factor of variability. So if we cannot really say that unbiased siya, kay wala siya bias. Na siya bias na component which is x prime x inverse. This happens when do you think this happens? Na siya anin na component. When your x is what? Kanus ani na ana component kining x prime x inverse? When do you think? Any idea? Ang usual man gud nato, well, beta hat conditioned on your x is usually normal beta sigma squared ra na siya I. Pero pag naay x, ang x naay dili satisfy, naani na component kining x prime x inverse. Kanus ana siya. Unsay dili i-satisfy sa x. Any idea? Napa mo?
Yes,
Yes,
ma'am.
ma'am.
Unsa inyong idea? Kanus ani siya. Ang usual man gud nato kung natay beta hat, unbiased na siya, beta sing maay. Mao man na ang mga assumptions sa inyong linear, di ba? Linear models katong mga error term or ang imuhang mga y's. Sigma squared I ra gyud na siya. Pero naani na component kining x prime x inverse if unsa man. What do you think? It has something to do with x. Kung ang imuhang design matrix is not full rank, no? Dili siya full rank. Then the variance will be inflated. So it will not be an unbiased estimate. The MSE is a component of the variability plus a bias, no? Full rank, not full rank. Kung dili siya full rank, diha mo gawas ang component na kay multiplying factor sa imong variance. So now you know. So also, unsa gani ni atong V? The V is this one, the variance. The V for ordinary least square is a component of a variance conditioned on X. On your explanatory variable will be Wishart, no? So mo ni ang general na formula Wishart, pero when Q is equal to 1, it boils down to a W1, but W1 actually is a chi-square, no? Chi-square distribution. So it will just boil down to a chi-square central. So these are the application of this important lemma. Okay, so that's it for the important lemma. And then I will discuss this on Tuesday na. So the Tuesday topic will be section 17.5. So again, if you look at the topics there in your book, chapter 17 is actually just until 17.8. So Tuesday 17.5 naman ta, Wednesday I will discuss distribution t-square, the Wishart distribution, and the functions. So you will expect next week by Friday will be the first exam, no?